Good morning and welcome back. Today we will talk about the last part of chapter 11 and we will finish our discussion about the special relativity. Okay, last time we talk about, go back to page section 3, covariance of electrodynamics. I just want to show you that the electromagnetic laws do not need any modification because they are already covariant. That means they are invariant in uh, Lorentz frames, in all the Lorentz frames. But it's not very clear from the very beginning, so we have to change the format a little bit. Next page. For example, conservation of charge. Slightly change, define a full current. We got the conservation of charge. And obviously it's invariant. It's covariant. That in all the Lorentz frame, the form is always the same. But we define a full current. And then we define a full potential. From full potential, we know the Lorentz gauge will be invariant. Will be invariant in form. And wave equation for the vector potential and scalar potential also invariant in form because they are the four tensor of the same rank, first rank. So they are invariant in form. But this time we define four potential. Then we can define four wave number. Four wave number includes the old Ks, Ky, Kz, and a new. So what will we have? The four wave number can be written into this form. Four wave number inner product of four position. So we got this one, and this one give us this one. That is invariant of the phase. This relation, this one is covariant. Okay, pretty good. What else? We can then define field, but field has 6 components only. Therefore, we will use a second rank anti-symmetric field strength tensor, this form, okay? And F alpha beta and subscript F alpha beta superscript, they differ in here. Here, negative, positive, negative, positive. Okay. And from this relation, we got the first one, divergence F. That's a tensor. And this one is the tensor of the first rank. Therefore, we should correspond to the first rank for vector. Okay? So we got this one, these relations. From this one, we got this one. And then this one. So from this inhomogeneous equation, we got two Maxwell equations. And then the homogeneous equation, this one, we already proved. This one gives us 0. If this one is 0, then it will always be 0. This relation gives us another 2. This one and this one. Gauss law for magnetic field, Faraday's law. Okay? So from Gauss law and Faraday's law, we got 2. So for Maxwell equation, we only need 2 tensor of the first rank first rank plus tensor, 4 tensor of the third rank. That's the third rank tensor. Okay, what else? Okay, so now we know the field tensor. The field tensor, these two give us the four Maxwell equations. And we know the component can be transformed, should be transformed according to the Lorentz transformation matrix. Therefore, eventually, we find these relations. Parallel electric field is the same before and after, not before and after. In this frame and in this frame, parallel to the motion will be the same. Parallel the magnetic field will be the same. So this part and this part. So in here, actually, not the vector is just one component. Okay. And here we got another one. Electric field in this one is correlated to this one and this one. On the other hand, magnetic field is correlated to this one and this one. I should use a laser pointer. Okay. What else? Remember, we have a conservation of energy and conservation of momentum. So today we will talk about conservation of energy and conservation of momentum. No, not yet. I still have to emphasize one more thing. That is force equation, Lorentz force, rate of change of the energies. Okay. Next one is the conservation law for field and mechanical energies. Okay, as mentioned in Jackson chapter 6, equation 111 and 122, we got these two equations. This is conservation of energy, and S is the Poynting vector, and conservation of momentum, mechanical momentum, field momentum, and from the stress tensor, Maxwell's stress tensor. So first, we should define how to prove. Actually, in your lecture note, we use a blank room to cover this area. You should prove this area. Try to learn this part by yourself and to write it down, because this proof is not a complete proof, just a partial proof only, not a complete. So you should prove, if you are interested, you should prove by yourself. Maybe you will have a chance to see this question in quiz number 2. Okay? That's a hint. You should study in advance. First, let's define the symmetric stress tensor. Theta, superscript alpha, beta. 1 over 4 pi. G is metric tensor of known tensor. Alpha mu, F mu lambda, F lambda beta. So that's the first terms. Second terms, 1 over 4 G alpha beta mu lambda. Subscript, superscript from equation from chapter 12. Okay. I do not give you a complete proof about these two equations, but you should, because some of the material will be shown in chapter 12. So you should study, you should have the ability to study by yourself. That's my expectation. After giving you the basic understanding of electrodynamics, you should have the ability to study the rest of the chapters by yourself. Chapter 12, chapter 13 by yourself. Okay, so from these different definitions, we got this one. We can write into this form. And this form, for beta equals 0, we got this one. U probably comes from here. And pointing vectors comes from here. E cross B or E cross H. And that's E squared plus B squared, something like that. Okay, that's for this one. And for this one, we have a field, lambda. For beta equals 0, beta equals 0, we have ES, EY, EZ. Therefore, that is current source minus J dot E. Okay, got it. That's the conservation of energy. The others, 1, 2, 3, conservation of momentum can be seen from these equations. Quite similar. Quite similar. So you should prove this part by yourself, especially conservation of momentum. Prove conservation of momentum from these relations. From the relations, it's an extra point. So if you can derive, please upload your files to ILMS. It's 2 points because it's not very easy. So it's 2 points. You can let me remind you again. You can write anything related to electrodynamics to me. Upload to the ILMS system. That's extra point. Quite important. Okay, I will give you 2 special case and 2 problems. So after this page, I will show you 2 special case. The first special case is let's consider. Actually, these 2 special cases are related to chapter 14. The first case is the linear accelerator. The second case is something look like synchrotron radiation. It's related to undulator and the wiggler. So consider the general form of the relativistic equation of motion. So let's general form the change P, the time change rate of momentum equals the force. So the force is any force, Lorentz force, gravitational force. And in this case, P equals gamma mv. And first, let's consider the force is in the same direction as P. Let's consider P as a force as the driving force and see what will happen. If these two are the same, we can simplify into intensity, magnitude only, gamma mv reduced to 1 dimension, okay? So gamma is obviously related. Gamma time change rate can be write into this form. And then eventually we got this one. So gamma cube V over C squared minus so V over C squared dV over dt. And then next one, gamma m dV. So we have gamma dV dt. Okay, Then gamma m here, so the 1 correspond to this one. Gamma m dv dt 1, and gamma cube m v square over c square. So we have extra terms here. But remember, we can simplify this one. This one, gamma is equals to this one, so v squared over c squared plus 1. Plus 1 give us cancel. Eventually, we have this one. That's gamma squared. Interestingly, gamma squared, v squared over c squared plus 1 equals gamma squared. So eventually, we have gamma cubed times m dv dt. So the force will related to gamma cube ma. It's not m times a, not the old F equals ma. In this case, F in special relativity, and the force is parallel to the velocity, then F equals gamma cubed ma. That means the constant force does not cause constant acceleration. Okay, that's news. Newton doesn't know. Special case 2. If we give it a perpendicular force, what will happen? Since it's perpendicular force, so gamma do not change, as in the circular motion. In the circular motion case, the force is always perpendicular to the motion. Okay. In this case, the driving force equals dp, the p change rate, time change rate, gamma mv. So it's gamma m. Gamma is a constant, m, of course, rest mass constant, and dv over dt. So for another case, perpendicular case, force equals gamma ma. That's for perpendicular. So for perpendicular force and for parallel force, F at low frequency, at low velocity, F equals ma. At high velocity, F could be F equals gamma ma or F equals gamma cube ma. Okay, so that's new information, new knowledge. Now, I will give you two examples, two problems. We know there is the Doppler shift. I will show you the Doppler shift. The first case, Doppler shift. We have a police radar operate on a frequency of omega. Operate on a frequency of omega. What's the frequency received by the police after the speed is reflected from a car moving at the velocity v0? So police send a signal omega k, and a car move in a velocity v0. And this is the direction of the signal. Let's assume the police is at rest. He is hid behind a tree and he used a laser gun. A laser gun sends a signal omega k here, and the car move along the highway. Okay, so the car move along the highway. Therefore, there is an angle difference, theta. Okay, and there is an angle difference. The signal laser signal hit the car first and then reflected back. The frequency will be different. We can measure the velocity from the frequency difference. Okay, that's the idea of radar speed detector. They make a lot of money. The police, our police, receive the fine 51% of the money from overspeed detection, overspeed ticket. OK，罚单，超速罚单。In a police frame, the radar sends a wave, a frequency omega, and wave number k toward the car, which is moving at velocity v0. Directions shown in the figure. We can transform omega to the car frame first using these equations. So omega prime received from the car or detect from the car is equals to gamma 0 omega minus v0 kz. Kz is the component of k, so kz equals k cosine theta, the rational cosine. Then substitute everything here, clack, clack, clack. Eventually, we got, also, we know k is related to omega over c because it propagates in the free space. So we got gamma 0 omega 1 minus v0 cosine theta divided by c. Okay, this part should be small. This is the Doppler shift frequency detected by the car. Okay, it's also the frequency of the wave reflected by the car as seen in the car frame. So step 1 is police send a signal and car receive the signal. Step 2 will be the car frame. The car reflect the signal back to the police. So omega prime equals gamma 0 omega 1 minus v0 cosine theta over c. And once again, the car reflected back to here. And we can draw another figures. This figures means the wave k prime, but angle, since they differ by an angle theta, v0. In a car frame, the car is moving at velocity v0 relative to the car. Transforming omega prime to the police frame, we obtain the frequency shift by the police. Let's Doppler shift again. So second frequency, reflected signal. We can write into this form, omega prime minus kz prime. So once again, omega move to the front. Omega prime move to the front. Gamma 0 omega prime. And here we got these relations. So we have omega prime substitute to here. So eventually we have gamma 0 square omega 1 minus v0 cosine theta over c square. Since compared with the speed of light, car move very small. So this term is very small. For any moving object on Earth, very small. So therefore, omega can be approximately equals to 1 minus 2 v0 cosine theta over c. Gamma 0 is very small, close to 1. If the radar frequency is 1 gigahertz, the car moves away from the police at a very high speed. Then the frequency shift will be minus 200. That is the red shift. If the car moves toward the police, that will be a blue shift. Okay. Second problems. Let's That's the first part. The first part. Second part is actually we studied this before, but now we will use a different perspective, different approach to find the solutions. That is, an observer in the laboratory frames laboratory. He sees not he or she sees an infinite electron beam, a lot of electron beam of radius A, and moving a uniform charge density rho from the laboratory frame, moving actually at a velocity v0. What force does he or she see on, on an electrons at a distance r? This time r is smaller than A. So he see within the beam, not outside. Maybe we can change to outside. Let's hint again. If I ask you what happened, what force does the observer see on an electron at a distance r outside the beam? Okay, that will be maybe from the axis. Assume the electrons move actually at the velocity v0 that move in z directions. So we can have two frames. This is laboratory frame, and this is a rest frame of the electrons. Okay, two viewpoints. We should obtain the same result. So first, the problem can be readily solved in the left frame. In the left frame, it's easy because we will take a long route for an exercise on some of the transformation equation just derived. Actually, how to calculate this one? We have charge, so we can use Gauss law. This one. From Gauss law, we can obtain electric field. And we have current, we can use Ampere's law and omit this one. Because constant motion, steady state, so no this term. So just one, Ampere's law. We can readily solve in the left frame using Gauss law and Ampere's law. But now we will take a long route, 比较长的路. The purpose is to study the transformation of these equations. First, the current density Jz in the left frame is Jz equals rho V0. And we have in the beam frame or rest frame that is moving with spin. Moving with spin, we got Jz prime equals gamma z, Jz minus Vz rho. So if we move with the beam, you will no current move, no charge move. Charge are fixed. Okay, and rho prime will be gamma 0, rho minus V0 c squared, Jz. So eventually we got rho over gamma 0. Therefore, in this frame, the charge is dilute because divided by gamma 0. However, in this frame, the charge is increased. That's because length contraction. Related to length contraction. Total charge should be the same. but because of length contraction, so density will be increased. We see that the left frame rho is greater than the beam frame by the factor gamma 0. This is because the unit length of the beam is contracted, the length contraction by this factor when viewed in the left frame. Okay? Next step, we have Jz equals 0. We have rho prime equals this one. We can calculate in a beam frame or the rest frame. We can calculate electric field first. And how to calculate electric field? Gauss law. Gauss law. But this time we should use prime systems, since we are interested in a region below the radius A. Below the radius A. So we can use Gauss law, 2 pi r prime er prime equals 4 pi times pi r prime squared times rho. That's the volume, not volume, cross section times rho prime times L times L. We got everything. Okay? So er prime equals 2 pi rho prime r prime. And rho prime is here. And r is perpendicular. Therefore, r do not change. So er prime equals 2 pi rho times r over gamma 0. You might be wondering what happened here. That seems to differ from what we know in chapter 123. Chapter 123, we do not have 2 pi and we have epsilon 0. But in this case, no. What happened? Because this is a Gaussian unit. Gaussian unit. Gaussian unit. We talked about Gaussian unit last time. If you don't understand, just go back to Jackson or go back to the end of last semester, last lecture, last course. Okay, that's video. We now transform. We have electric field, and in this case, no magnetic field because beam frame, everything is at rest. So we can transform from the beam frame to the left frame by using the reverse transformation equation, in which V0 equals V0 EZ. Okay, reverse the transformation equations. So we got E perpendicular equals gamma 0. Reverse the transform. So eventually we got 2 pi rho times R. Okay, that's in a laboratory frame. And B, this result will be the same as Ampere's law. The same as Ampere's law. Okay, so we can start from the Ampere's law and the Gauss law easily. Or we can start from the beam frame and use Lorentz transformation. They should be the same. In this case, there is no reason to transform from that frame to this one because this is easy symmetry. However, in chapters 14, such a transformation is required because we have other components. Other components is not that simple. Okay, so eventually the force F on an electrons in the left frame is, this is not this is the lowercase f. In the old time, in previous chapters, F denotes as the force per unit volume. But we define F as the force on an on an electron. So F equals minus E plus 1 over C V cross B. Once again, SI unit, Gaussian unit, Gaussian unit, Gaussian unit, Gaussian unit, and eventually we got equals minus 2 pi E rho gamma, rho R divided by gamma 0 square, ER. So the force will be in the R directions. The force will be in the R directions. So there is uh, uh, there is an attractive force because the minus sign here. Attractive force to focus the beam. That's interesting. Let me see. Attractive force. We might expect it's a repulsive force, but now we have an attractive force. Why? We have attractive force. Okay, that's very interesting. Attractive force. If you can explain why the force is attractive, okay, let's once again as an extra point. Please study. You can study by yourself. Okay, so today I will end here. That's the end of chapter 11. And we have some homeworks. We also upload the homework video to you, except maybe chapter 19. Chapter 19 is not upload, but uh, we will upload the solution for problem 11.19 soon. So next time, we will have a quiz number 2. And once again, quiz number 2 will be a take-home exam. Take-home exam. I will give you the problem of quiz number 2 very soon. However, the final exam will not be a take-home exam. It will be an open book exam, but not take-home. We will reassemble at our classroom. At our classroom, okay? So you should study. You should study hard. Okay, that's the end. See you next time.